Hello, and welcome back to the course on distributed systems and security. This will be the third video on consistent communication. So recall that what we're looking at here is starting with a network which have unorderly delivery, for example, a flooding network, and then trying to create order in message delivery. In this video, we'll be taking a look at how to implement total order. However, to do that, we need to recall what is causal order. So it's been a long time since you saw video 2. Maybe go back and take a quick reminder what causal order is. But just very briefly, causal order means that if two messages could have affected each other, then they will be always delivered in the order of the effect. So if A could have influenced B, then A arrives before B at all parties. Okay? And we saw how to use vector clocks to do that elegantly and efficiently. So what we want to do today, or in this video here, then is to take a look at how do we ensure that all messages arrive in the same order at all parties. Now, that doesn't imply actually that they arrive in a causal order, but what we will do today is actually implement a network which have both of them. So it has causal order and total order. Okay? And the reason why I need you to recall what causal order is we will assume that we're communicating on a network with causal order. And then we'll just focus on how to order the concurrent messages, which might come in different orders at different parties. Okay? So I skip forward a few slides now, forgive me. Part 3, total order. So here's an example where we don't have total order. Let's say we send 3 messages at the same time. Let's say we are delivering messages locally the second we send them. And of course, I mean, here we have that the order of delivery at party 1 would be M1, then comes M3, and then comes M2. So M1 in particular was first, whereas down here at party 3, we have M3 first, then M2, and M1. So everything is completely screwed up. We also can see in a figure like this here, right? If we want to deliver these 3 messages, M1, M2, and M3 in the same order at all parties, 2 of them will have to wait with delivering their own message until they receive messages, the messages from the other parties. Okay? So this is what we earlier called delayed local delivery. So you cannot just deliver your own messages when you send them, because something else concurrent might be on its way, and we might all agree that that should be delivered before your message. So let's have a look at how to resolve a situation like this and deliver these 3 messages here in the same order. So the first thing we will do is to agree on the order in which messages should be delivered, assuming that we have a global view of the system, okay? So let's not, for now, be confused about whether messages are on their way or not. Let's just say we have a global view of all messages. What order would we like to deliver them? Okay? And the one I picked for the course is the following one. First, you take all messages, and then you deliver them in a causal order. So if A caused B, you always deliver A before B. Then this will now leave us only with concurrent messages being a problem, right? Because if 2 messages are causally related, they will be delivered at all parties in that order, right? So conveniently, we just use an underlying causal network for solving that. Now it could be that 2 parties, A and B, send messages at the same time, and then they get exchanged, so they are concurrent. In which order should we deliver these 2 messages? And the one I picked is simply to take the lexicographic ordering on vector clocks. Okay, so we just say something like 0, 0, 1 is smaller than 1, 0, 0. Like 1 is less than 100. Think of it like that. Just go through them position by position. and look, is A less than B on the topmost position? Yes, then it's smaller than. If they're the same, you look at the next position, the next position, the next position. If they're different, then there will be a position where the first position where they differ, and then take the one that's smallest there. That's the smallest vector clock. So we just say for the concurrent ones, just order them according to that, and then gives us a total order now. Right? First order according to causal order. Anything that's still outstanding, order them according to lexicographic order. Are we done? No. So what we have so far agreed on is in which order messages should be delivered if we have a global view of the system. Okay. But the problem is we don't. And to illustrate it, let's have a look at party 1 in the setting here. So we have 3 messages M1 and M2 and M3 being sent. We take a look down here. This one has vector clock 1, 0, 0. This has 0, 1, 0, and this one has 0, 0, 1. So this is lexicographically the smallest message. So in this system here, the messages should be delivered in the order M3, then M2, then M1. Okay. What about up here? Well, there's 2 messages. This one has vector clock 1, 0, 0. This has vector clock 0, 1, 0. So up here, the messages should be delivered in the order M2, then M1. Okay? So up here, M2 gets delivered first. Down here, M3 gets delivered first. The problem is, if we take a look at the system from the point of view of party 1, the systems are the same. Okay? So at the point where party 1 received M1 and M2, which is this point in time, if it's in this system down here, it has to wait because M3 is on its way and it has a smaller vector clock. However, up here, party 2 at this point needs to deliver M2 and then M1. It cannot wait for M3 because it's not on its way. Okay? So liveness and safety is battling each other here. Up here, P1 should deliver M2 or it will be waiting forever for M3. And there will not be liveness, it never gets to deliver M2. However, if it delivers M2 up here, it also delivers M2 down here because the system looks exactly the same from the point of view of party 1. And therefore down here, party 1 would be breaking safety. It outputs M2 and then a second later it learns, shit, I should have outputted M3 instead because it just arrived and it has a smaller vector clock. Okay, so it looks like party 1 have to pick between breaking liveness or breaking safety. Yeah. So that's the only system, that's the only thing we have to combat now, right? We agreed on what the order should be globally, but we don't always know all the messages. So we don't know when a message is safe to deliver, so to say, right? At this point up here, M2 is safe to deliver because there is no M3 on its way. Down here, it's not safe to deliver. So how do we solve that? I used safe slightly wrongly on the previous slide, just erase that, because we also have a technical definition of safe. And the way we'll go about it is to define a criterion which will make it safe to deliver message. In particular, this criterion will ensure that there are no concurrent messages on its way. Okay? So think about that, that if I have a message and I know there are no messages concurrent with this message on its way, then I'm actually ready to find out where should this message be in its order, right? Because everything that's in its causal past already arrived because we're using causal communication as the underlying network. And therefore I know how to arrange it with all those messages. I mean, they already arrived. So the only thing that could be outstanding is where should this message be in position to concurrent messages. But if I'm ensured that all messages that's concurrent with this message arrived, I can just order them on their vector clocks and I will know exactly the position of this message. And then when we reach that position, when I delivered everything before it, I will deliver this message. Right? So that's how to deal with it. Just somehow magically guess when for a given message when is no concurrent message on its way. Okay. Here's a criterion that will allow to do that. So I will call a message M sent by P safe if the following holds. And this is slightly, it kind of the other way around from what you would expect. So pay attention. I wait until from all other parties I received a message M prime, I've received another message, and that message is in the causal future of this M here that I'm considering. Okay? So I have a message, I wonder, can something concurrent be on its way? I don't know, but what I will do is I will wait until I receive from all other parties something that's in the causal future of this message. How could that be? I mean, one way of thinking about it is I had this message, right? And then let's say I send out a ping message. So I send a message to everybody. And then when they get that message, they send me a message back. So it happened that after I received this message, I sent something out and get something back. Then this message here, of course, is in the causal future of this one, right? Because there was tuk, tuk, tuk. So somehow, to call a message safe, I wanted a signal to go out from me to everyone else and come back again. Okay, so that's the point in time I will call this message here safe. And then what we will do is simply take the set of all safe messages and then order them according to this ordering we had. So first we order them causally, and then we order them according to vector clock, and then I can just deliver all of them. The trick being, I will not get a surprise and having something concurrent arrive later. So let's see that this is actually the case. Okay, so let's see that if a message is safe, then there is no concurrent message on its way. Put differently, if a message is safe, then any message that is or was concurrent with that message already arrived. It might have arrived after it, but it already arrived. At the point where I call it safe, I received everything that was concurrent with it. Okay. So theorem, if P comma M is safe, then there is no message P prime M prime prime concurrent with P comma M on its way. Okay. Okay, so I'm going to do a proof by contradiction. So let's say I have a message from P prime called M prime prime, which is concurrent with my safe message here, and which is still on its way. Okay, this is what shouldn't happen. So let's assume for now that it happened. See if we can reach a contradiction. So there's this concurrent message here from P prime on its way. Okay, so let's consider P prime. Remember that my message M is safe, which means that from all parties, I receive something that's in the causal future of my safe message M. So I also received that from P prime. So let's call that M prime. Okay. So let P prime comma M prime be the message that I have received from P prime, such that it is in the causal future of my safe message here. It must be out there. Okay. So I know that P prime comma M is in the causal past of P comma M is in the causal past of P prime comma M prime. Let's establish one relation more. I also know that P prime comma M prime is in the causal past of P prime comma M prime prime. Why? Well, because I have assumed that this thing here, P prime comma M prime prime, the message M prime is still on its way. Okay, from P prime. Whereas this here, P prime comma M prime, that's also a message from the same P prime, and I already received it. And remember that we're using causal communication as the underlying communication network. So that means, I mean, first of all, two messages coming from the same party, they're always causally related. And therefore, I will also always receive them in that order in which they were sent. Right? And since I have a message here, one of them was I already received, and the other one is still on its way, it must have been sent after the one already received. Because otherwise I got two messages from the same party that swapped, and that is not allowed. We have causal communication, which implies FIFO. Okay? So I know that this M prime here, which I already received, is in the causal past of the message M prime prime, which is already on its way. Then I have established two relations now. M is in the causal past of M prime. M prime is in the causal past of M prime prime. And then we just use the simple fact that this thing is transitive. So it follows that M is in the causal past of M prime prime. Okay, so that's what I set down here. M causal past M prime causal past M prime prime implies that M is in the causal past of M prime prime. But then clearly M and M prime prime are not concurrent, because concurrent means that neither of them is in the causal past of the other one. Okay, so I have that these are not concurrent. But I started the proof by assuming that M prime prime and M are concurrent. Okay, so by assuming that they were concurrent, I can prove that they're not concurrent. So the assumption is false. So there is no concurrent M prime prime, which is still on its way. Okay, read it in the book, go over it again. You can see that it makes sense. It's a little bit slippery with all these tricky errors there. Okay, but what the takeaway lesson is that if a message is safe according to this way that we defined it here, which is nice and operational, then we can deliver it. Then we can already just order it according to everything that's on disk, and if it's the next one, we can deliver it. Okay, and this thing here we know how to implement efficiently. We saw that with vector clocks in the previous video. Simply just keeping track of vector clocks and then checking when the vector clocks are less than each other in all position. So we know how to do that. Okay, that's it. Except it's not, because the system I described you, it is safe. It will never make a mistake and deliver a message in an order where it shouldn't be delivered. But it's not live, right? Because remember, I only deliver message when it is safe. What if it happens that some message never becomes safe? And this happens all the time. I mean, in particular at the edge of newly sent messages, and in particular if there's no more communication in the system. Take a message here like M3. This is the first message that should be delivered. It arrives up here at P1 at this point here. So M3 up here becomes safe only when P1 received from both of the two parties something that's in the causal future of M3. So what should happen from this point on for M3 to become safe is P1 should get the idea to send a message. It should arrive at P2, and then something should arrive back. And also P1 should send something that arrives at P3, and something should come back. At this point, M3 is considered safe and it can be delivered. Okay. By the way, we can use the figure also to go over the proof again and see why is it that if I send something, let's say I'm considering the safety of M3, if I send something here and get a message back, why is it that guarantees that nothing concurrent is on its way? It's because when this thing comes back, because we're using causal communication, it's pulling along everything in its causal past. And if this message here had something concurrent down here, let's say M3 here, right? It has M2 here sitting that's concurrent. If I send something here, boom, that will be in the causal future of M2. So when it's sent back here and gets delivered, it must force M2 to be delivered also, because we deliver stuff in causal order, right? So everything that's concurrent out there, I send a message out, get it back again, and then I pull all the concurrent stuff with me, because it's forced to be delivered before the message I sent out. That's what's going on with that. Okay, so how do we avoid that a system like this here deadlocks if there's no more communication? Well, we just create more communication. So what we can just do is lightly use time and just say, now and then, if I haven't seen communication for the last second, I will send out a heartbeat. I send out a ping and get back an egg is another way, right? So up here, if too long time travels and I cannot declare M2 here safe, I will send out a ping to everyone, and everyone that receives my ping have to send back an egg. And at the point where I get the egg, something went out and came back again. So now I have something from everyone in the causal future of my message. So now it's safe. Now I can order it and I can deliver it. Okay. And that's it. Thanks for listening.